Hello, hello. Okay, so we were dealing with this breadth first search. Okay, and the twin algorithms, that is BFS breadth first search and this DFS depth first search, having plenty of applications in real life. Okay, or in computer science or in other fields. Okay. So these two are the most fundamental algorithms. Okay, and why you are less in number today? Still you are celebrating. Okay. In the last class we have seen, okay, this breadth first search can be utilized in communication network. From here, if you want to send packet to say Amazon, okay, say with how many hops you can move from here to here. Okay. Say this is NIT Durgapur router and this is the first outside say Delhi, and then from Delhi to say USA some server. Okay. So this hop you can detect these hops using the breadth first search algorithm. Okay. What? You? Hmm? Sorry? Water? Now another example is this Kevin Bacon numbers. Okay. So there is one website, the Oracle of Bacon. So this guy is this Kevin Bacon, and he is a renowned actor. Okay, and say I want to see that what is my Bacon number. That means how closely I am associated with this guy, actor, this Bacon. Say I have if somebody has acted, say this guy is Bacon. This guy is Bacon, right? With a smiling face, this guy is Bacon. And say this guy having associated with this Bacon directly, that means he or she co-acted with this actor Bacon in a movie. Okay. So he or she was associated directly with one movie, directly with Bacon in one movie. Directly. Okay. And say now this guy, consider this guy, right? Now this guy is not directly associated, but this guy is directly associated with this guy in a movie. Okay, right. So if this guy is directly associated with this guy, then his Bacon number is 1. But if this guy is not directly related, that means it needs 2 hops to go to Bacon. So his or her Bacon number is 2. Okay. So like this way, say this, I can link up that whether I am having any relation with Prime Minister Modi. Okay. Our Honorable Prime Minister Modi ji. Okay. So maybe I know I don't have any direct connection. I know somebody in Delhi. Okay. I know really somebody in Delhi. And then that guy, this Delhi guy, is directly means having connection with our honorable prime minister. Okay, I mean whoever be the prime minister at that time. Okay, so in that case, I can think of my prime minister number. Okay, or Modi number is 2. Okay, so like this way it goes on. I mean, we can fit that Bacon number philosophy in other context as well, right? So this is the idea, and so this find the shortest hops from any arbitrary actor or actress with Kevin Bacon. That is what I am looking for. Okay. So in this case, this breadth first search will be coming into picture. Okay, with how many hops I am going to Bacon. So that will be my Bacon number. Okay. So it may be so happening that this I am related with Bacon like this also. Now another this philosophy is highly right now this breadth first search algorithms or this problem is under some serious research. Okay, there are there are citation networks. Okay, how many citations I am having. So all these things are coming into picture. Another interesting idea that is with this Kevin Bacon, our academic counterpart also we are having. This is actually this thing. This what is the Bacon number? This thing actually originated with this Erdos number. Okay, so this guy Paul Erdos. Okay, he is one of the greatest mathematicians world has ever produced. Okay, Paul Erdos. How many of you have heard this guy's name? Can you raise your hand? Who has heard this guy's name? Then you haven't studied mathematics at all in your HS level. If you are not hearing this guy's name, this guy is absolutely famous. Okay. So one of the uncanny characteristic this Paul Erdos had, he was bachelor throughout. Okay, right? He didn't he didn't marry. So this guy was a free bird in that sense. Okay, and Paul Erdos. Okay, so he used to go. He initially he was not associated with any of the universities. He used to go to one of the professors, renowned professors in one of the universities, and he told that guy that hello professor, I want to work with you for 1 month or so. Then that professor could be highly obliged because Erdos is the renowned person. He is trying to work with him. Okay. So he was telling that yes, why not? So you where to stay? Okay, you stay in my house. So then he used to stay in his house, And then he wrote one good paper in collaboration with that guy. And then after that paper is over, he used to go to another place. Okay. Another university professor he was searching for. Then he worked with that. Okay. Then Paul Erdos, Paul Erdos had many, many papers in collaboration. Okay. Many papers. And the thing is that 70% contribution of that paper is Paul Erdos. Is going to Paul Erdos. Right. So now these people started looking that, okay, many people had some kind of direct connection with Paul Erdos. Okay. So this, no, I should be writing neatly. Right. So this guy having a direct connection, this guy having a direct connection, this guy having a direct connection, this guy having a direct connection. But then people started thinking that, okay, if I am writing a paper with this guy who had a direct paper with Erdos, then what is my Erdos number? Okay. So from there, the concept of this number is coming. That means number associated with a very famous guy. Okay. How much closely I am related with that. The more I am closer, the more I am uh, I may be getting a good job because if this guy is related with this guy, then this guy is almost a famous one because he has worked with Edo. Okay. If somebody is working with Einstein and I am working with that guy, then maybe whenever I'll be giving my biodata to anybody, then I'll be easily picked up. Okay. So the more I am having more number, more Erdos number, that means I am not that much famous. Okay. So this is this we can think of this thing. What is my Erdos number? Okay. The shortest hop I can reach to this Erdos. That we can find out with this BFS technique, breadth first search. Okay. So now let us see the algorithm of breadth first search. Okay. So this is the Kevin Bacon graph, okay, one of the graphs. You can go through. So this is Erdos number. So this is the graph related to Erdos number. Okay. Now we are going to this algorithm BFS. Okay. So this is from CLRS, you see. Okay. So in this BFS, what we are trying to do is for each vertex U belongs to this graph G. And except the source vertex v minus s. Okay. So g dot. So here in CLRS, this is g dot v. Okay. G dot v means all the vertices in the graph. We are representing that way. In CLRS, it is represented like that. Okay. Now this g dot v minus s means all the vertices except the source. Okay. The source vertex. So here, this may be the source vertex. Okay. So you have to identify a source vertex, and from there you start calculating. Okay. Now this for all the vertices except the source, what we got to do is recording on. Yes. So for all these vertices, u dot color, that means all vertices we have to color white. Okay. So in actual implementation, this white kind of thing is not there. Okay. So maybe you can represent that u dot color. Okay. So that thing, maybe you can think of, say, -1 is white, -2 is red, -2 is black, -2 is gray, -3 is black. Okay. So here we'll be using three colors. One is white, one is gray, and one is black. Okay. Right. So this u dot color is white means in actual implementation you can represent white as -1. Say gray is -2, something like this. So u dot color is equal to white. Means it is still unexplored. Okay. All those guys, all those nodes to be unexplored, all these nodes are still unexplored. We haven't explored it. Okay. And then u dot d. U dot d is the distance from that vertex, from that source vertex to that u, that we are initializing with a very large number. We don't know what it would be eventually. Okay. So initially we are thinking that from source vertex to that vertex, the distance is very large. Okay. Then it will be updated whenever we will be running our algorithm. Okay. Hello, you guys. Hello, are you listening? And then this u dot pi, okay, u dot pi equal to nil. So this is the parent pointer, okay. So this parent pointer, I am coming to it, okay. And then this s dot color equal to gray. So the source vertex, where from I have to start, that vertex, we have to make it gray. Okay. So you see it is gray in color. Is it visible? Gray in color. So this is the vertex which is gray in color, right? And then s dot d. S dot d, that means source to itself, its distance is, we are initializing 0. And it will be remaining 0 because from node to node itself, it's 0 distance. We don't have to move. Okay. And then s dot pi is nil because that is the initial vertex. It should not be having any parent, right? So it should be nil. And then we are maintaining one queue as and when we will be exploring vertices, we will be putting those vertices into the queue. Okay. So you are maintaining one queue. So queue is for initially, queue is initialized with null. Okay. Queue is initialized with null. We can write queue equal to, say, null, or we can use this notation. Okay. So this arrow, null, it is initialized with null. Okay. So nothing is there. No nodes will be there. Okay. And then what we are doing is we are starting from a source vertex. So we are enqueuing that source vertex into the queue. Okay. We enqueue that. Okay. Right. So this is the queue we are maintaining first, and the source vertex. We are, so this is our S here. We are enqueuing S here, right? And this is the source. The distance is 0. Okay. Distance we are measuring here in terms of number of hops. Okay. So this is one hop. So this is one hop. Then this is two hops. If I am reaching from here to here like this. So now this while Q is not empty, while Q is not empty. So initially we are having S in the Q. So Q is not empty. So we are entering in this loop. Okay. And now what we got to do is we are dequeuing this Q. Okay. So whichever is in front in the Q property, you know. Okay. So whatever is in front, that will be taken out. Okay. So only one vertex is there, S. So that vertex will be taken out. Okay. So you will be now initially, whenever the first iteration going on, you will be this S. Are you getting? Are you getting? Huh? No? Sorry? So you come this side. Here. Come this side. Here. Can you see board? You? So you are not seeing boards and you are not coming this side. And then what is the utility of attending this class? Can you see board? Huh? Are you getting this? Why? Why S will be dequeued? Tell me. You. Huh. Why S will be dequeued? Or will it be dequeued? What is enqueuing? What is dequeuing? Do you know? What is that? Huh? Sorry? Not hearing. Can't hear. Okay. Are you getting? Huh? You? You. Huh? You? Getting? What is the utility of dequeuing this? S? Huh? This is? The way you tell in front, inside the field of oval, na? Huh? The way you tell, okay? That way you tell. Can you hear me? Huh? So that way you tell. I am not using mic, but I can reach you. Huh? Why S is DQ? Okay. Sit down. Acha. What is your name? What is your roll number? 139. What is your roll number? What is your roll number? 193. What is your roll number? 140. So S is the sole element in the queue. So this will be DQ. Okay. And now this S we are exploring. Okay. Now what we have to do is we have to search all the adjacent vertices of this S. Okay, all the adjacent vertices. So here what we can think of that this S, if this is the S, all adjacent vertices we have to explore now. Okay. After exploring all these, we will be exploring all these vertices for the next level. Okay. So this is the main philosophy of this breadth first search. We are starting with this, and then the first level, all the adjacent vertices will be exploring. But in the next one, which will be coming up, that is the DFS, where first I have to take this, and then I have to take this, and then even exploring these two, I have to go exploring this guy. Say I'm going from here to here. Okay. So from starting from here, I'm going deeper and deeper into the network. Okay. Even exploring this, the adjacent vertices of this guy. So that is the main difference between this BFS and DFS. Okay. Okay. Now what we are doing is for each V adjacent to this U, adjacent to this U, that means U is S now. Okay. So here, not here, here, we are here. Okay. So if V dot color equal to white, okay, V dot color equal to white, then V dot color will be equals to gray, okay, and V dot D will be equals to U dot D plus 1, and V dot pi will be equals to this U. And then we have to enqueue this V, node V. Okay. So we are here, now we will be here. Okay. We will be here. What we are doing? So this V, say this guy, in any arbitrary order, say this is our S, this is our S. Okay. We are here. And we are having two adjacent nodes from here to here. So this is the adjacent and this is the adjacent. That means a direct connection we are having. Okay. So these two nodes we are exploring now. Okay. So these two nodes. Okay. So say I am breaking ties. Which nodes? Which V will be first explored? We are having two nodes. Say lexicographically we are breaking ties. Lexicographically. Okay. That means in alphabet wise. Alphabetically. So maybe this R will be coming first. Okay. Then W will be coming next. Okay. Right. Or you can think of reverse order. W will be coming first and then this R will be coming. Okay. So maybe say this CLRS they are doing like this. W is coming first and then this R. Okay. So V will be W first. V will be W adjacent to this U. So V dot color. If V dot color is white, so we haven't visited yet anything. So it is white. We have initialized it white. Okay. Then what we got to do, V dot color will be gray. So you see this V dot color is, this is the V. So V dot color is becoming gray. Okay. And then V dot D, that means the distance of this V distance of this V from the source vertex S. Okay. So source vertex S is equal to U dot D. So our S is U now. U dot D is 0 and plus 1. So 0 plus 1, that is equal to 1. Okay. So you see this W having inside this we are having 1. Okay. Written 1. If we are zooming in. Okay. Are you with me? I can call anybody in the blackboard. Okay. I'll be giving one example. Okay. And then you will be solving. So please pay your attention. And then marks will be there. Continuous assessment will be based on that. Okay. And then this guy is explored. Okay. So this, okay, it is still not done. So we are V dot D equal to U dot D. And then V dot pi is equal to U. That means how I have gone here, I have gone here in this node through this S directly. So I'll be having, say this, I'll be having a parent pointer like this. Okay. So this V dot pi equal to U means I am having a parent pointer like this. Okay. So this parent pointer, okay, this parent pointer implementation in many, say, if you are going through Karumanchi and other things, so then you won't be seeing this parent pointer kind of thing they are implementing, okay, in breadth first search, and then you will be having some aha moment there, okay. But you remember that this parent pointer, if I am doing this, it will be helping in many analysis that we are that we will not be exploring in this class. It will be helping in many analysis and it comes in many applications also. If I am using this parent pointer, one of the immediate implication is that if we trace it back, then from here to here, which are the nodes is on that path. If I am tracing that, the exact, let's say each of these is a Facebook network. Okay, so say this the name of, if I am tracing, say if I am tracing from here and then here, okay, so then on the way of tracing I can extract the corresponding name of that node. Okay, that means corresponding friends of that recommendation. Okay, so that parent pointer implementation having lots of application in the analysis as well as in many different problems. Okay, so this V dot pi will be equals to U. And then what we got to do, we have to enqueue this V, because this guy, say this U, say this W, we have to enqueue here in this queue, right? So you see this S is dequeued. So Q was, after this Q was momentarily Q was null. And then whenever I have explored this W, this Q is becoming W first. Okay, right? So the first adjacent node I am exploring, and then this is uh, this type of update we are having. So it was 0, and then this is 1. Okay, that means I can reach from this S source vertex to this by one hop. Okay, by one hop. Now this control will be going back to here and it will be checking whether there is any other adjacent vertex of U is there or not? Is there any? Is there any? Which one? Which one? Left one. So this guy now. Okay. So we had this S that is equal to U, and then we have explored this, and we have put this into this Q. Okay. Into this Q, and then this one is also the adjacent of this U. So the loop is still going on. Okay. Right. So this loop is going on, and then this R will be explored, and it will be made gray. Okay. And then this R will be incremented. V dot D will be equal to U dot D plus 1. What will be the value of this? 1, because U dot D is 0. From the source vertex, its distance is 0. Okay. So 0 plus 1, it will be 1. Right? So then this R will be entered into this Q. And then V dot pi means right now R dot pi will be equals to U. So we'll be having another parent pointer like this. Okay. Right. So from here, now what we have done, we have explored this vertex fully. This vertex or this vertex. This vertex we have explored. All its adjacent edges, that means adjacent node, not edges. Adjacent nodes we have explored. Okay. Right. All. So now what we are doing, U dot color will be equals to black. That means it is freezed. Okay. Its exploration is done. Right. So that's why it is, we are having a black node here. Okay. Right. And then what we got to do, we have done this. We have done this. So this U equal to S, we went back to this loop. Everything explored, and now the control will be going back to this while loop. Okay. And then it will be checking whether Q is empty. Is Q empty? How many nodes are there? 2 nodes. Which are those? These 2 nodes? W and R. Okay, so this W and R we are having. So this Q, W will be explored next. Okay. So the W will be explored next, and its adjacent vertices will be explored. So now this guy we are exploring. Okay. So now this from here I can explore. So we are having, whenever I am exploring this guy, so this is our W. We are having 3 adjacent edges. Are you seeing 3 adjacent edges? So this is our S, and this is already black. Okay. Right. So whenever I say this is 1, okay. Now I can explore this node if V dot color equal to white. Can I explore this? Because V dot color means V at that time will be S. Okay. So V dot color is not white. So I should not explore because this is already explored then. Okay. Now I have to explore this. This is still white. Okay. This is white. Hello, are you getting? Huh? Are you getting? So why I am not exploring, I cannot explore. Can I explore this guy? Yes. Can I explore this guy? Yes. From here? Why not? What is your name? Huh? It is already visited. What is your name? Huh? Sorry, what? Ritam. Ritam. Roll number 173. 173. So now this 1, so it will be 2, okay? And say this, its parent pointer will be what? This W, okay? So now this will be what? Number here? 2. Because I am coming from here, 1 plus V dot D equal to U dot D plus 1, okay? So this 1 plus 1, so we are having this here, this is 2, okay? So this is, this U will be what here? Can you tell me? In this iteration, U is what? U is W. Okay. So U dot D was 1. Okay. 1 plus 1, that's why it is becoming 2. This is becoming 2. Okay. Right? And now everything explored. So now this will be black. Okay. So like this way, this breadth first search will be going on. You complete this analysis. Okay. Right? Analysis means you complete this procedure. Okay. Okay, so today up to this, tomorrow we'll be analyzing its complexity and then we'll be discussing this DFS.